Question number 5. Alright, so question number 5. You are given, consider the wave function that is given by psi of theta. So psi is a function of theta and what? At the same time, psi is a function of phi. So at the same time, it's a function of theta, and it's also a function of phi. Be clear. It is given by 2 sine theta cos theta e to the power I phi plus half sine squared theta 2 to the power I phi. 2 I phi. So express phi theta phi as a linear combination of spherical harmonics. The linear combination of spherical harmonics. What are spherical harmonics?
So does this question likely come in the examination? Does it come?
What are you saying?
I'm saying that this question, does it always come in the exam like the one?
Where will it come?
The previous one that we did on Tuesday. Okay. You said question 4 always comes in the examination.
What are spherical? The first time we have never heard about it.
What?
So I am referring to spherical harmonics.
I know about
what you understand by spherical harmonics.
I know about harmonic oscillators. Because we did that last year.
Can you hear me now? Hello?
Yes, I can hear you properly. I think
Okay,
the network on my side.
Yeah, I can see that the network is poor. But anyway, let's try to manage. See how it goes. So here on question number 5. So as a linear combination of spherical harmonics. So when we refer to spherical harmonics, we are just referring to any surface that is defined in terms of r, theta, and phi. So we must define this spherical harmonics in spherical coordinates, which is r, theta, and phi. So what do we mean by this? If it's a spherical harmonics, it must be, we are writing that psi in terms of r, theta, and phi, for example, like this. So the keywords of spherical harmonics, you must take note of it. So for psi, remember psi is a function. Psi, that phi and theta. Psi, theta, and phi. We want to write this in spherical harmonics. In other words, spherical harmonics we are referring to. We are rewriting that expression terms of spherical harmonics, which means you want to rewrite it in terms of psi of r, theta, and phi. In other words, this should be the same as that r, capital letter R, is a function of small letter r. These are what we are referring to as the spherical harmonics. So we are rewriting in such where r of r is the radial part, which depends on distance from origin. So this r of r is dependent on origin, the radial part. Whenever you see that r of r, they are referring to the radial part, the distance from origin. So this is the distance from origin, the radial part, r of r. So you'll be measuring the distance from the origin, the center, radius. Right. And also the spherical harmonics describe that wave function. So in other words, this wave function, the general spherical harmonics, if you want the spherical harmonics, which means it's y of L and M, we are going to write it in terms of theta and phi. So this y of M is written in terms of theta and phi. So which can also be written, I will explain the symbols, M, and then P multiplied by P, LM cos, and these formulas must know them. Cos theta, e to the power I, M, phi. That is our y of L, M, which means, and what are those symbols going to tell us? L always deals with the angular momentum. So whenever you see L, R cross P, so L, where we are crossing angular momentum. So whenever you have angular momentum, L, angular momentum, that is your L, the angular momentum. And momentum is P. Right, so the angular momentum, it ranges, the angular momentum, it ranges from minus L to L, positive L. So this L which you are referring to, it ranges. So you must know that this L which you are referring to, it only starts from 0, 1, 2, and so on. So whenever we are saying YL1, which means the spherical harmonic when L is 1. So L ranges from 0, 1, 2, going onwards. But M, that one was angular momentum. So M is the magnetic quantum number. So whenever they talk of M, they are referring to the magnetic quantum number. That is the M. So M is the magnetic quantum number. And that magnetic quantum number, it ranges from what to what. So the magnetic quantum number, M. M always starts from minus L. So if you want the value of M, it's equals to, it always starts from minus L up to. So where does this end to? It ends to positive L, the angular momentum. So the magnetic number, magnetic quantum number always ranges from negative L to positive L. And your L, the angular momentum, ranges from 0, 1, 2, which is the orbital angular momentum. So this one, not the angular momentum, small letter L, which is the orbital in the orbits on grade 10 work, whereby the electron spin is positive and negative. So this one is the orbital angular momentum. When you are talking of Pauli's exclusion principle, in the orbitals, there is a negative, positive spin and negative spin. That is what we are referring to as the magnetic quantum number. And then the Legendre polynomial, where you see PL. PL is the Legendre polynomial. So whenever you see this PL, we are referring to the Legendre polynomial, PL, this P. So the P is referring to the Legendre polynomial. All right. So we indicate that P, L, M, and we are having magnetic quantum number in the orbital quantum numbers. Angular momentum, quantum number. The magnetic quantum number, M. Angular momentum, the orbital angular momentum quantum number, and the magnetic quantum numbers, which is M. So the polynomial PL, this is what we are referring to as the Legendre polynomial. That is the P. These are just the definitions of the formula so that you are aware. So we have that P, and also we have the N, the normalization constant. When we're normalizing that time, wanted to get a 1, finding the normalization constant. So that N is standing for the normalization constant. So that N is standing for the normalization constant, NLM, which is the normalization constant. So you must know what each symbol means there. So the spherical harmonics. So whenever we talk of spherical harmonics, we are referring to YL. That function, it's YL. This is the spherical harmonics. Whenever we are talking of spherical harmonics, YLM of theta phi. All right, YL of theta phi. So we are going to use that example so that we calculate the answer. So now we have determined. So now we have our psi. Our psi is in terms of theta and phi. So there we are supposed to identify your normalization constant, the polynomial, and so on. All right. So let's start. Number 5. So this is the question for number 5. We are given that function for number 5. And the question clearly indicates for question 5 that we are supposed to express this function, this wave function, as a linear combination of spherical harmonics. So let's start with that. So this is the wave function that we are supposed to express as a linear combination of spherical harmonics. So you express psi, which is the wave function, as a linear combination of spherical harmonics. What is the relevant spherical harmonics, which means we are checking from what we are given here. You check with the standard equation for spherical harmonics. If you check here, right? So you check the value of the L, and then you check the value of the M. So here you can see Im. Can you see? E to the power Im phi. So which means you already know the value of M. You already know the value of M. And if you know M from the range which I was explaining here, if you know M, L it's minus M is equals to minus L and positive L. That is your M. So that information, you get it from the equation. That 2, it tells you that that is the M. So you have your M already there. Your M is the 2. Your M is the 2. And
Hey, can you please explain that again? The M and the 2.
if you compare the equation here, right, we are looking for YLM. So YLM theta phi. So I've given you the standard equation of a general spherical harmonic. So the standard equation of the general spherical harmonic is this one, which I have given you here. YLM. This is the standard equation for spherical harmonics. Can you see it? So if you are already given the wave function and you're supposed to write it in spherical harmonics like this, so you identify your M, check the complex number. The complex number should be M, and it's I. It's because it's raised to the e to the complex number I. Then the M is the one that is multiplying the phi, that phi at the end. So you check your equation and try to relate what is the number M, what could be that number M from the equation. Okay. You are now we are still identifying our M, the magnetic quantum number, which is M. We are identifying M, which is the magnetic quantum. Is it clear? We said the M is the magnetic what? Quantum number, isn't it? And then this M, it ranges from negative L to positive what? L. Yes. So the value of M, it starts from, so if you say M is 2, so if M is 2, which means if I want the value of L, the L will start from M is 2, so which means minus 2 to 2. That will be the value of my M, minus 2 to 2. So which means minus L to positive L. Right. So you have your M here. This is our M, which we are already having. We are already having an YLM. So this is your L. This is your L, and this is your M. Your L, your M. Right. So you have 2. The spherical harmonics, when L is 2, what is the value of M? When L is 2, what is the value of? And then here, it's ranging. So e to the power I phi. By e to the power I phi, which means you can see that the magnetic quantum number is 1. If it's e to the power I m phi, what will be the value of M there? What will be the value of MIV? Remember, from the general equation, this part, which is raised to the exponent, if e to the power I m, M will be 1, because we are saying e to the power I m phi is equals to e to the power I phi, which is there on the equation. So if I'm to ask you, what will be the value of M? M should be equals to what? 1. That's why here the M, which is there on top, it's a 1. And the magnetic quantum numbers, which is L, that L, the magnetic quantum numbers, which we are going to calculate. We said the L, which M is 1, indicated M is 1. So if M is 1, which ones are the magnetic quantum numbers? Which is we are looking for L. From minus L to positive, it will be what? Negative
1 and positive 1. Positive 1.
negative 1, positive 1. Then how many? But L range is also 0. 0 is also part of the L. Remember, we said 0 is also part of the what? Of the L. 0, 1, 2, 3 is also part of the L, of the orbital quantum numbers. And the magnetic quantum numbers, M, is the one that is ranging from negative L to positive L. So in that equation, once you have identified, remember this is our original equation that we are having in terms of phi. And then we have the relevant spherical harmonics, which is y21. How do you get y21? y12. If M is 1 and L is 2, you substitute in this equation. What do you get? For example, if you have the spherical harmonics y22, now the quantum numbers, this one is M and we have L. Now your M is 2. If M is 2, now we have a different spherical harmonics because the M, this M is now a 2. The M is now a 2. Right. So from the first equation, we are getting, what are you going to get from the first equation? When you rewrite this first equation and you want to write it in terms of sine theta cos e to the power I phi. So the reason why you are taking this, you are trying to get this variable, sine theta cos theta multiplied by e to the power I phi. So you make that subject of the formula. So which means you are just rewriting equation 1. So from equation 1, everything goes to the left. And remember, you are just solving for sine theta cos theta e to the power I phi. You are just rewriting the first equation. And from the first equation, sine theta e to the power I phi is equals to negative root of 8 pi over 15 multiplied by y1, which is the spherical harmonics, where ml, the m is 1, l is 2, this equation. So you are rewriting this equation, which is here. That is what you have done. So you rewrite that equation. So you indicate the value of y1, y2. And then now it's 8 pi over root of 15. And before it was 15 over root of 8 pi. So you are just playing with the mathematics. Are you getting it? Hello? I mean, this equation, you are rewriting it, this equation, you are rewriting this to get this equation. So this equation, you want to be left with only sine theta e to the power phi. So let's do it together, bit by bit, so that you don't get confused. Hello?
The y, those two equations, the y where we have 1 and then where we have 2. That equation, are we given that equation? Y2 to the power 1 The
Are you given what?
the spherical harmonics.
For the spherical harmonic,
Mm. So I'm lost.
you mean for this equation for the relevant spherical harmonics, where m is 1?
Yeah.
Okay. So you substitute in the original equation, mine. What is the value of m? M is 1, isn't it?
Mm.
And then L is what?
Positive
So the original equation is this one. So if you substitute m equals to 1 and then L equals to 2 in the spherical harmonics formula, which is this one. Right. So from the original equation that you are given, that's where you are substituting the values. Are we not getting 18 pi? Try to substitute and tell me what you are getting.
well, I'm substituting 1.
Yes. You are substituting what? You want to get this value where it's sine theta 15 over 8 pi, and the value of m is 1 and the value of L is 2. Where we are getting the values, spherical harmonics 1, 2, these are the standard spherical harmonics. You hear what we are saying? The standard, this one which is here, you do not derive them during exam. You get what I'm saying? Because your question is, where are you getting y1, y2? This one, isn't it?
Yeah.
Yes. So the answer is that they are the standard spherical harmonics. So if I tell you y1, y2, you should be in a position to tell me that y1, y2, it's plus or minus. It's plus or minus root of 15 over 8 pi multiplied by sine theta cos theta e to the power I phi. It's like a formula.
I must know it by head.
It in an exam they give you, don't memorize that.
Oh.
They are obtained from a general definition, or they can be provided in a formula sheet.
Oh.
So in a formula sheet, yes, you take this one. So it's only a matter of you to pick. They will give you many of these spherical harmonics and then you choose. Like, for example, let me write it down. These are the spherical harmonics so that you get the standard one. They are given on the formula sheet. That's why I was saying download some question paper so that you can see which formulas will be provided and how we are going to use. So check now. For L, if it's for L equals to 2, if your L equals to 2, now you want to know which ones are your spherical harmonics. So for L equals to 2, the standard spherical harmonics for L equals to 2, the standard spherical harmonics. So you'll be using that YL always in the spherical harmonics. They have the spherical harmonics, they have different formulas, which are And we are only talking for L equals to 2. All right. So you have Y, which is the spherical harmonic. And remember, it's L, it's ML. ML. Right. So in our case, we have an L equals to 2. So these are the standards. If the first one, which corresponds to L equals to 2, we find out the spherical harmonics is 0. And the answer there, it will be the square root of 5 over 16 pi multiplied by 3 cos. And these ones, we are given the formula minus 1. And then the other spherical harmonic, whereby M, now L is still 2, but M is either positive or negative. That's why it's positive or negative 1. Positive or negative. So this, when L is positive 1, that one on top, the corresponding one, it will be a negative. That's why it's negative, positive. The signs are always different. So it's just saying when M is negative, this side, this sign becomes, so it's 2 of them. So positive, negative, and then it will be square root of 15 over 8 pi multiplied by sine theta cos theta. Then e to the power multiplied by e to the power. We check the sign. If it was positive, and also this side it will be positive. Positive I phi. So it will be I multiplied by phi. Then the last condition is whereby we are having y, the spherical harmonic 2, L equals to 2, which means my M is positive or negative 2, which is equals to the square root. So in an exam, you'll be given the one that is going to be used. So you don't memorize or derive these expressions, like what you ask. Like, where are you going to get this? From the formula sheet, which is sine squared theta multiplied by e to power positive, negative 2I phi. And the positive, negative, it's saying if you choose a positive M, then your sign is still going to be positive. If you choose a negative, then it will be negative. So it only changes the sign for the M equals to positive, negative 1. So I have given you this one. And you must check. We said if your L is 2, the range of the L in terms of M. So check. If your L is 2, which means it's starting from minus 2 up to what? Up to positive 2. Because your L is 2, minus 2 up to positive. And that magnetic quantum number, it will be 2. Magnetic quantum number, 2. So the value of L can be negative 2. The value of L can be positive 2, negative 1, positive 1, and also 0. Those are the magnetic quantum numbers for L. So if you have M equals to 2, the magnetic quantum number, if M is equals to 2, then my range for L, I know my L will start from negative 2 up to positive 2. Then you go negative 2, negative 1, you go 0, then you go to 1, then you go to positive 2. So these are all the positive values for what? For L. So you'll be looking for each of these L. You are looking for each of the spherical harmonic for each of the L. So M is the magnetic quantum number. It's not changing. It's 2. But the value of L can be 0. then you have a different magnetic quantum number, spherical harmonic. And then you have another spherical harmonic, M is still 2. Then you go to, it can be positive or negative 1. So we have chosen a different one, L, which is positive, negative 1. And then the last one that is left is positive or negative 2. We have a different spherical harmonic, a formula, which is 2 and positive and negative 2. Any question? That is what we are doing in terms of this spherical, which formulas we're using. So if you know that your L is 2, if you know that your L is, then those are the spherical harmonics that you are going to be using. And the question now is, how do you know? How do you know that the L is equal to 2? That is my question. How are you going to know? How do you know that your L, the L value is equal to 2? In our question, how do you know that L is equal to 2?
Are we not? Is it not because the original equation is 2? I was about to ask you the same question, and then
How do you know that? Because we are talking of L equals 2 here, and how will you know that the L value is equal to 2? Where are you going to see that information? All right, let's go back to the question.
so we are still not doing number A, ne?
Yes. It's number 8. These are harmonics. These are the last part of the quantum, these ones, which are a bit challenging.
Hey,
But once
I'm seeing
you know,
flames. Oh.
yes, but once you are done, one question, isn't it, you have not done this one?
Mm. Hush. So Monday, can we start with question 5? I would try to check the video and then see, because
It's
I
not,
honestly,
you must also check the notes as well. The one
yeah.
which then you see where the L and where the M is coming from. So if you come here from the formula of spherical harmonics, like that time when I was asking, how do you know? If you come here,
Isn't
on
it
the
because
origin,
the 2 is given there on the equation? The 2
oh,
side.
yeah, that's why we have Y, ML, and then M is the one that is there. And then the L is what you need to know, which means the polynomial, the normalization constant, and M and L, for M and L. And if you check the polynomial PL and R, PL and the Legendre polynomial and the normalization constant from the equation, the Legendre polynomial and the normalization constant. So you check, there is a psi there, there's e to the power I phi plus half sine squared e to the power 2I phi. So your question is that M, remember on that equation, it's in terms of psi. So you want to know what will be the biggest number of your M, which you are going to get. So the M value that is going to be the biggest there is M, which is equals to what? To 2.
To 2. So you're taking the formula that is given there,
Yeah.
and then you're plugging it into the spherical harmonic.
Yes.
Okay.
So the thing that you must know first is the general equation of a spherical harmonic. Like how does this one? So that you can identify. Then from there, you pick the value of M and L, of M and L. So you are finding that in the equation, you still have M, which is positive 2, which is the highest, and you have another M in the equation, which is 1. So which means you now know the range of the M, which you are working with. The range of the M, which you are working with, it's from minus L to positive L. So what is the value of L? From the equation, I'm seeing that my maximum M is what? The maximum M is 2, the biggest M from this equation. The value of the M is 2. Can you see it? Here, the M.
M is to sine squared.
Yes. And then here, M is what? Is here, M is 1. So where are you ranging the M?
Sorry,
So which means this.
You check the E, that I.
That E, the exponent I, it tells you that the range of the M minus minus 2 up to 2. So if you are ranging from minus 2 up to 2, which means your L becomes what? Your L becomes automatically what? 2.
2. Oh, because M range from negative L to positive L.
Yes, M ranges. So after that, then you come to the equations. We have the general equations of the what? Of the spherical harmonics. So that if your L is 2, how do you put it? L is 2, I use this one. And this one will be given in an exam. For example, if your L is 3, if your L is 4, what will be the equation? They differ, isn't it?
Oh, the L is the M is the upper value and the L is the one downwards.
Yes, the M is the upper value, the L is the one.
Oh, now I'm starting to understand now. Hey, physics. Oh.
You must continue with the problem where we have ended. Try to look at it so that when you are discussing it, you follow up. Now at least you have a bit of an idea how to look at it. And then now you can try to follow that example for A.
Oh, yeah. The last week video is on the 16th and then 21 Tuesday and then 23. The one for today.
16, 21. You say 16, 21?
And 23 today. So those are the videos that you need to send. I'm not sure if you're gonna send all of them tomorrow when you already downloaded this one, or you're gonna send this to tomorrow.
Yeah, it will be morning.
Okay, I'll just send you a text to remind you tomorrow.
All right.
Okay. Yeah, because I think the videos are gonna be important.
Go through that, then you see, because you can't rush. I will be just talking. I just to be able to give you that introduction because you very harmonics. Yes, that's why sometimes it might take a bit of time, but at least when you've got the concept, you can try to follow up because you'll be surprised. When are you getting the spherical harmonics 1, 2? They are coming from the what?
From the equation you were given. Oh, okay.
Yes.
Okay, so.
All right. So you look at it, then you continue from the explanation.
Okay,
and
I have gotten to.
So that we can start preparing now.
Yeah, I was saying I haven't forgotten to send the question papers. I'll still send. Just that I didn't find time today.
No problem. All right, let's stop here for today. We'll see each other on Monday.